think what I have to do first is do a quick job. Quick job offers toggle help tips on or off. Use on the map, select the discovered city to see the available job offers. Let's start there. Select the job offer. Price, sort by. Use this one to see if they prefer at the top. What is this? Expiration. $11 kilometers. 0.67. How about 7? And then take a job. Love it. Wait, hold on. Luxembourg. Wait, hold on, man.
From extraterrestrial intelligence.
And travel.
In Contact, the heroine, Eleanor Arroway, who's a radio astronomer engaged in the search for radio signals from extraterrestrial intelligence. Well, she receives a signal. And the signal, after much decoding, turns out to be a machine. And the machine is a means of traveling great distances.
Inside the machine, a space traveler would sit in what looked like an ordinary armchair. In the movie of Contact, the chair went high-tech, but the idea was the same. A mysterious machine designed by aliens that would transport a human across the universe. But in writing this story, Sagan ran into trouble. Our galaxy is so large that it would take his heroine thousands of years to reach her destination.
That was my problem, to get her to a great distance away from the Earth and the Milky Way galaxy to meet the extraterrestrials and come back and do all that within the lifetime of the people she has left behind.
What Sagan needed was a shortcut through the vast reaches of outer space. And this search would unravel the secrets of time travel.
In the early 1980s, there was a common misunderstanding that you might be able to travel from one place to the other in the galaxy without covering the intervening distance by plunging into a black hole. But there was something about the whole idea that made me nervous. And it was for that reason that I contacted Kip Thorne.
Kip Thorne was an old friend and an expert on black holes.
I was a little upset because he had the heroine in his novel traveling through a black hole, and I knew that you can't go into a black hole and come out somewhere else. The fundamental laws of physics forbid it.
A black hole form.
Okay, a ver. World map. So gotta get out of here. No, ya ni me acuerdo de los keys. Okay. How do I turn this on? This on. Do I have no HUD? Pero creo que sigue en movimiento, ¿no? es para acá, era para atrás. No tengo ningún shortcut mapeado al volante, creo. Me pasó en alto. Ah, chinga, ¿se me apagó? What? Job details. Cargo used plastics 9 tons. From Luxembourg, cell plant to Antwerp, Euroflow's ports remains 9 hours. Estimated arrival 3 hours 57 minutes. Job income 2,700. Mandatory break in 10 hours 12 minutes. Damage 0. Local regulations. Expressway, motorway 90. Oh yeah, 90. Okay, 90. Status controls. Vehicle control. Parking brake, right turn. Left turn. Agudo. What the fuck is agudo? Button 23. Options. Okay. No, not yet. Oh, yeah. So this is where I could have activated the what's it called? Cruise control now. Now, what I want to know is how can I my location F. ¿Cómo puedo poner widgets like the fuck? System. Desktop backgrounds. What the hell? Save. Save game. Sure. New save. First quick job. I don't know what I'm doing. But like, how do I place it in my HUD? You know? Gameplay. Sequential, yeah, that's fine. Vehicle stability. Kind of suspension stiffness. Suspension stiffness. Braking intensity. 5. Ah, creo que es aquí, ¿no? Run, no, HUD. Key navigation speed warning. A15E42. ¿Hasta dónde es? Trip time 248 kilometers. ¿Cuánto llevo explored? Explore. Puta madre. A ver. Media. Audio player. Music player. Stream save. Game radio. Radio stream. Pop gear. No thanks. Mira. Qué locotrón. A15E42. No.
When a large star dies and collapses to a small, infinitely dense point with immense gravitational pull. This warps space so severely that everything nearby is sucked in and destroyed, making travel through a black hole impossible.
If you go down through the horizon of a black hole, at the center you don't find a tunnel that leads you to some other place in the universe. What you find instead is a region where the material of which your body is made, the atoms get stretched and squeezed beyond recognition. And then space and time themselves get stretched and squeezed beyond recognition and destroyed. But if you've gone inside a black hole trying to travel through it, that doesn't matter. You're dead. There was no way you could get through.
I got back a long letter from Kip with about 50 lines of closely reasoned equations, which was a level of detail in response to my phone call that I had not anticipated.
Rather quickly, I recognized that what he probably should do is replace the black hole as a means for rapid interstellar travel with a wormhole. At that time, wormholes were not something that were part of science fiction. They became part of science fiction as a result of this interaction between Carl and me.
Wormholes are like tunnels in the fabric of space and time, predicted by Einstein's equations. Thorne realized they might hold the answer to Sagan's dilemma.
Our universe, it's three-dimensional, but we can pretend it's two-dimensional, so it's like this sheet of paper. And we live in Pasadena over here, and London is over there, and it's thousands of miles from Pasadena to London. This universe is curved up so that through hyperspace, the distance from Pasadena to London is only a few feet. And there is this pipe, this little wormhole, that will lead us from Pasadena to London across that very short distance. And it's like looking through a crystal ball. You see a distorted picture of what is going on at the other mouth of the wormhole, which may be in another galaxy, or it may be near the Star of Vega, or it may be in London.
This shortcut was just what Sagan's heroine needed.
I must have gone through a wormhole.
Contact had started something new.
It introduced to the world to science fiction, and also reintroduced to serious scientists the notion of a wormhole as something that was really worthy of thinking about.
With wormholes on center stage, Thorne soon found they had other mysterious properties. They could be used for more than traveling great distances in space. They might also be used for time travel.
If you have a wormhole, then you can turn them into time machines for going backward in time. We thought, how could we have been so stupid? We should have realized that. That's obvious.
What became obvious to Thorne was that time could behave in strange ways inside a wormhole.
Let's suppose that I have a wormhole with one mouth here and the other mouth over there. Now, there are three different possibilities for how time could be hooked up through the interior of that wormhole. The first is that when I stick my arm into this mouth, it came out over there simultaneously. The second possibility is that when I stick my arm into this mouth, it comes out over there only after some delay. And the third possibility is that if I go into this wormhole mouth, then I come out over there before I ever even go in. Let's just see that. It was quite a surprise when I realized that with a single wormhole, you could have time hook up toward the future or toward the past, and that you could actually manipulate the wormhole and change how time hooked up. That was a surprise, but a very satisfying surprise when I really understood how it worked.
Suddenly, time travel seemed feasible. At least in theory.
As a youngster who was fascinated by the possibility of time travel in science fiction, to be in any way involved in the possible actualization of time travel it just brings goosebumps.
A physicist working on the possibility of travel into the past has to be careful not to be labeled a crank or accused of wasting public money on science fiction fantasy.
Doc? What's the word? Stand back! In less than 3 minutes, I shall have escaped this age of madness!
Nevertheless, it is an important question.
Right now, we are in one of those classic, wonderfully evocative moments in science. When we don't know, when there are those on both sides of the debate, and when what is at stake is very mystifying, very profound.
Time is something which at a fundamental level we don't understand.
Newton, of course, thought time was like a river that flowed.
Time is the thing out there that flows, and I go with the flow.
Time is nature's way to keep everything from happening all at once.
It is one of those concepts that is profoundly resistant to simple definition.
We continue with the sale of Albert Einstein's manuscript for the theory of relativity.
Einstein's theories of relativity are invaluable because they lay the foundations of modern physics, including the possibility of time travel.
One of this catalog, and I have a bid of $2 million to start the bidding on this, and $2 million now.
In his theory of special relativity, Einstein declared that time can be altered by speed. The faster you move, the slower time passes.
$3 million at $2,300,000.
In 1971, Joe Haefele and Richard Keegan put the theory to the test. They flew 4 atomic clocks around the world to compare the passage of time on an airplane with time on the ground.
I don't trust these professors who get up and scribble in front of blackboards claiming they understand it all, because I've made too many measurements where they don't come up with the numbers they say.
Richard had told me that in all the previous work he had done, he had never seen the effect of time dilatation.
I had
never seen it.
I knew what was being predicted, and it always seemed to me that the best proof is to measure it.
Measure? Well, hopefully it's going to be of the order of...
To see how time slows down with speed, they had to fly all the way around the world in the original experiment. Today's atomic clocks are more accurate, so the warping of time should be apparent even on an ordinary transatlantic flight.
But just wait and see. One of these days, baby.
Glass of champagne for you, sir?
Yes, one for me and one for my friend.
Certainly. About 5 minutes past 4 local time, which is 5 minutes past 9 English time.
Einstein said time is that which is indicated by clock. I think I know what a clock is, therefore I think I know what time is.
Seem to be following an unbelievably constant track.
En route, they collected data from the pilot, then put it into Einstein's equations to predict the time change.
We have accumulated so far a change of 34 nanoseconds. Broadly speaking, it seems to confirm the original prediction. The clock will have gained somewhere between 37 and 40 nanoseconds when we land at about half an hour's time.
Suppose you would live for 100 years, and you would spend your entire life on one of these aircraft, flying around the world. You could expect to be younger than people who did not do that by about 1/10,000th of a second.
The UTC, USNL Master.
To measure exactly how much time changed relative to time on Earth, the clock on the airplane had been synchronized with the international standard at the start of the trip. Then it was compared to the same standard when it landed in the United States.
If we put other cables in here, that changes by...
The clock on the plane disagreed with the ones on the ground by 40 billionths of a second, just as Einstein predicted.
At $2,700,000 now. At $2,800,000. At $2,900,000. Here at $2,900,000. At $3 million. $3,100,000. $3,200,000. $3,300,000 this year. Don't wait back there. Fair warning now at $3,300,000.
But taken to an extreme, Einstein's theory that time slows down at high speeds has even stranger consequences.
This is sometimes described as the twin paradox. Two identical twins, one of whom goes off on a voyage close to the speed of light, the other one stays home. When the space-traveling twin returns home, time has dilated for him, that is, he or she has aged only a little, while the twin who's remained at home has aged at the regular pace. And here you have two identical twins who may be decades apart in age.
Applied to a wormhole, this curious phenomenon might make time travel possible.
There are several different ways to turn a wormhole into a time machine if you are a clever and infinitely advanced civilization. By an infinitely advanced civilization, I mean somebody who can do anything their heart desires, except they can't violate the fundamental laws.
What they could do is take advantage of the twins paradox and send one mouth of a wormhole on a voyage into outer space. As the wormhole mouth approaches the speed of light, time slows down relative to the wormhole mouth that remains on Earth. At the end of its high-speed voyage, the traveling wormhole mouth returns to Earth, where it can be picked up by its owner. Just like the twins paradox, less time has passed for this mouth of the wormhole than for the other end that stayed behind on Earth. The wormhole is now a tunnel, with each mouth located in a different time.
If I now go into this wormhole mouth today, I will come out of that mouth yesterday.
So in theory, an advanced civilization might turn a wormhole into a time machine. But the practical details are something else again. Where would they find a wormhole in the first place? The answer grew out of the work of Kip Thorne's former teacher.
I like to think of space and time as analogous to the ocean, and changes in it as analogous to waves on the surface of the ocean. But those waves, of course, don't show up when one's miles above the ocean. It looks flat. Then as one gets down closer to the surface, one sees the waves breaking and the foam. I see no way to escape the conclusion that a similar foam-like structure is developing in space and time.
Wheeler thinks the space between atoms is filled with bubbles. And this quantum foam, as he calls it, gives rise to incredibly tiny wormholes.
Let's suppose we begin at the size of Britain, and we squeeze ourselves on down smaller and smaller, past the size of a human being, down to the size of an atom, and on down to the size of an atomic nucleus. We're then halfway to the scale of quantum foam. We have to then begin at that scale and go on down. As much as we went from Britain to an atomic nucleus, we have to keep on going down. It's another 20 powers of 10 on down. We get to a minuscule scale, far smaller than anybody has ever been able to reach with experimental apparatus. And there, the fundamental laws seem to tell us there must be quantum foam. Space, as we know it, must cease to exist in this smooth sort of a way and must become something more like a froth of soap suds. This quantum foam we can think of as having bubbles, but we can also think of it as having little handles like the handle on a coffee cup. That is a wormhole. It's something that reaches from over here in the foam to over there.
Thorne speculates that if quantum foam exists, an advanced civilization might be able to grab one of these tiny wormholes and enlarge it. But there's another problem.
We then had to face the fact that the one kind of wormhole that we knew as a solution of Einstein's equations was a wormhole that lives for only a very short time. It has a throat that expands, opens, and shuts in a flash so fast that anybody who tries to travel through it in that flash while it's open can't manage to get through. They get crushed in the pinch-up.
To travel through a wormhole, a human being would have to find a way to hold it open.
So we then ask ourselves, what is it that you need to thread through the wormhole to hold it open long enough for somebody to travel through it? And Einstein's equations told us the answer. We just had to do a page or two of calculation. What you needed was something very exotic, some material that has negative energy.
The bad news is that if you want a wormhole about 1 meter across, which is a really minimal requirement for something to put a human through, you need about -1 Jupiter's worth of this exotic matter.
So the repellent force of a planet-sized amount of exotic matter would be required to hold a wormhole open. But it's not as far-fetched as it might sound. Scientists have found that tiny amounts of such negative energy can be made in the laboratory.
Shown here, it supports this triangle.
All ordinary matter has positive energy, but exotic matter can be produced by squeezing energy out of a vacuum created in a tiny gap between two metal plates.
Now, when you bring two plates close together, photons of long wavelengths can't exist between the plates, so you exclude some of this energy from the system. When you do so, the energy between the plates is lower than the energy outside, and so there's a force between these two plates.
The force actually pulls the plates together, and that's critical because that tells you that the energy density between the plates has to be negative, and that is the key to it actually being exotic matter.
We just did it for fun, and it's built with just junk we found around the lab here. But in fact, we can measure an extremely tiny force with it.
That experiment, from our point of view, is a proof in principle that at least small amounts of exotic matter, effectively negative energy, do exist in the real world.
If enough negative energy could be collected, time tourists of the future might be able to hold a wormhole open long enough to make a safe journey into the past. Hoping that large amounts of negative energy might be possible, and speculating that wormholes could be extracted and enlarged from the quantum foam, Thorne took the plunge. He published his ideas about time travel in one of the most prestigious physics journals.
My concern was the word time machine in the title, and my worry was that the popular press would see this paper and would start to ballyhoo it in a manner that caused our serious scientific colleagues to pay no attention to it as being crackpot stuff. Very quickly, the rest of the press grabbed hold of it. Here we are, we've invented time travel. There are other stories that basically had us building time machines in our own basements. And I rather quickly pulled back and told the Caltech Public Relations Office I do not give interviews on this subject. I told my research group's administrative assistant I do not return telephone calls from the press on this subject. I will talk about anything else but not time travel.
But Thorne's work brought other scientists out into the open.
When I realized that my friend and extremely great scientist Kip Thorne published it, I immediately called him and told him, thank you so much for that. Now I will publish, I will work on this subject also.
He was overjoyed. on the other end of the phone. He said, "Oh, Kip, it's absolutely wonderful. Your paper's..."
Each level you gain a skill point. Long distance, high value cargo, fragile cargo, just in time delivery, vehicle driving. Bank, account balance 5,000. Loan offers. Skills. Email. Need money, we can help. Dear sir, madam. Local banking center for more information. Brand new DAF trucks for sale. Used trucks for sale. Long distance. Apply. Upgrades available. New items like bar wash. So another quick job.
Wonderful. You've broken the barrier. If you can do research about time travel, then so can I.
Igor Novikov had been working on time travel in secret for years. He was intrigued by the trouble that time travelers might cause if they went back and tried to change history.
Once it appeared that time machines were a real possibility, we then had to face the question of paradoxes, of going back in time and changing history, and thereby causing the foundations of physics to crumble beneath us.
You're in focus now, Paul.
Press the button, Harvey. Press the button, my friend. Send me back into time.
Time travel would seem to lead to contradictions if one was able to go back and change the past.
The grandfather paradox is a very simple science fiction-based apparent inconsistency at the very heart of the idea of backwards time travel.
If I have a time machine, then there is the danger that I may go into the time machine, go back in time, kill my grandfather before my mother is conceived so that she can conceive me.
Where does that leave you?
unlikely to get here.
Do you instantly pop out of existence because you were never made?
But then you couldn't have gone back, and so on.
Hurtling back through time creates paradoxes that have fueled dozens of Hollywood productions.
Dudes, you guys are gonna go back in time.
Anything you do could have serious repercussions on future events. Do you understand?
This is gonna cost me.
A serious consideration of backwards time travel must confront these paradoxes.
Billiard balls provided us a way to study paradoxes with time travel without getting into the nasty business of free will of human beings.
Billiard balls behave in predictable ways according to the laws of physics. Cause always precedes effect. But what happens if time travel is possible?
If I have a time machine, the story is quite different.
Imagine the pockets of this billiard table are the mouths of a wormhole time machine.
In this case, I have only one billiard, and I send that billiard ball into this mouth of the wormhole, and it will then come out of that mouth before it enters this one, hit itself, and prevent itself from going into the first mouth. Voila, a paradox. It's the billiard ball version of going back in time and changing history.
Of course, this problem was discussed a lot in literature, in movies, in science fictions. But I'm talking not about fantasies, but real science.
Having developed simple versions of the paradox, we then set about trying to figure out how to solve this. How will the law of physics behave if time machines are permitted? In searching for a resolution of the paradox, we were led by a principle introduced by Igor Novikov, which said that nature will only allow those behaviors that are absolutely self-consistent.
In order to be self-consistent, a ball emerging in the past must knock itself into the time machine so it can come out again along a trajectory that will knock itself back into the pocket. Novikov wrote mathematical equations for the possible outcomes of a ball hitting itself and found that a self-consistent solution always exists. This implied that nature would not allow a paradox to arise.
This is the main principle. All these events must be in self-consistency with each other. It's so simple, so obvious, but more of that, we gave the strict mathematical proof that this principle is the consequence of the basic ideas of the physics.
By the same token, Novikov's findings implied that the laws of physics would prevent a time traveler from rewriting history.
Yes?
I'm here to prepare your room, mein Herr.
What has happened has happened. It cannot be changed. It cannot be repeated twice in different ways.
Human beings aren't billiard balls, and we might like to believe in free will. So a sufficiently stubborn human would seem to be able to get around any sort of consistency condition by just demanding that he does something different.
I can have free will to walk along this wall without special key. It's my free will. Can I do that? No, I can't. Why? Because of the law of physics, because of the law of gravity. It's forbidden.
Laws of physics, like gravity, already restrain our free will. Novikov thinks these same laws would restrain the free will of a time traveler bent on changing the past.
The telescope, open up, please. Immediately.
If time travelers can't change the past themselves, could they alter history by sending a message into the past instead? Einstein's theories of relativity show that if something could travel faster than the speed of light, it could be viewed as going backwards in time. But relativity also says that's impossible. Yet this man may have taken a step in that direction because he claims to have sent information faster than light.
This signal is split into by an electronic mirror here into two parts. So we can compare the signal. One is moving through the air and the other one is moving through the barrier.
In this experiment, Gunter Nimst splits a microwave signal in two. Half goes through the air, traveling at the speed of light, and half is fired into a barrier to block the signal. But that's not what happens.
This is an oscilloscope where you see the signal and then we can see which one is faster.
The two humps on the screen are not in the same place because the microwaves that went through the barrier got to the detector first, apparently exceeding the speed of light.
Only this very small part comes to the other side. But it comes, and this part comes at a velocity which is much faster than the velocity of light.
So how could the microwaves go faster than light? And what was the role of the barrier? Nimst chalks it up to a strange phenomenon called quantum tunneling. At the subatomic or quantum level, the world is ruled by probability and chance, and the seemingly impossible occurs all the time. For example, when a stream of particles like photons meets a barrier, most bounce off, but a few of them materialize on the far side of the barrier and continue on the way. Nimst detected the particles that appeared and measured how fast they got there.
And used about this widgets for fun. And then we figured out that it's faster than the velocity of light. We did not think about its importance.
Another expert in quantum tunneling is Raymond Chow. He agrees with at least part of what Nimst has found.
In our experiments, we have measured that a single photon can tunnel across the tunnel barrier at 1.7 times the speed of light.
What bothers Chow is not that random photons seem to go beyond the speed of light, but that Nimst claims he can use tunneling to send information faster than light.
To have a genuine signal, you really have to control the signal. But in quantum mechanical tunneling, it's a completely random process. Fundamentally, we cannot send information with this tunneling particle.
Yeah, some colleagues were claiming that you cannot send information, and then we started to transmit Mozart 40, and this is, for instance, the original tape. That's what we sent at a speed of 4.7 times the velocity of light and a distance of about 14 centimeter. Whether you can recognize Mozart 40 or not.
Despite the randomness and uncertainty of the tunneling process, Mozart seems to have gone through the barrier.
The central question is, what is a signal, or what constitutes information? Has he really sent a signal, a sense of information faster than the speed of light? This is where Professor Nimst and I part company, because we don't really have a rigorous definition of what is information at the moment.
me that this is not information for American colleague, but for a British colleague. I think Mozart thought it was some information in it.
Transmitting Mozart is one thing. Convincing others that you've sent it faster than light is another. And so the debate continues, with neither side budging.
I insist on it that we have and we can transmit signals faster than the velocity of light.
NIMS has found little support for this claim. And few think this will ever allow information to go backwards in time. Still, the idea that time travel for people might become a reality raises a provocative question.
Time travel might be possible, but if that is the case, why haven't we been overrun by tourists in the future?
This argument I find very dubious. It might be that time travel into the past is possible, but they haven't gotten to our time yet. They're very far in the future, and it's the further back in time you go, the more expensive it is. Then there's a possibility that they're here, all right, but we don't see them. They have perfect invisibility cloaks or something. If they're so smart and such highly developed, then there's a possibility that they're here, we do see them. If we tell them something else, those ghosts.
I think that if people from the future were going to show themselves, they were to see more than me. What would be the point of revealing themselves only to prank the weirdos who wouldn't be believed?
But physics does put a limit on how far into the past a time traveler could go.
Relativity theory says in general that once you've made a time machine, you can never use it to go backward in time before the period when it was made. So there's no way I can use it to travel back to the age of the dinosaurs or even back to the time of my own birth, because I didn't make the time machine until recently.
So relativity forbids one of the most beloved scenarios of science fiction from ever happening, because you cannot go back before the point at which the time machine was made.
I don't have to worry about the possibility of my going back and killing my father before I was conceived. What I have to worry about is my grandson going back in time and killing me before he is conceived. That is, there's no possibility of changing our past, but in the future, one can change the future's past.
But there is a loophole that might still make even the most far-fetched scenarios possible. According to quantum theory, uncertainty and chance rule the subatomic world. You can never know the exact position and speed of particles at the same time. Instead, you can only give probabilities for their behavior. In a huge extrapolation, some people think that all these probabilities are occurring simultaneously. Anything that might happen actually is happening.
Quantum mechanics is a theory of many parallel universes. Some of them are alike, and some of them are very unlike. There are nearby universes that differ from this one only in the position of one photon or one electron. There are other more distant universes where we're not filming here at all, and there are others where I was never even born.
This is a radical interpretation of quantum mechanics. But David Deutsch finds the evidence he needs for parallel universes in a well-known physics experiment.
I first saw this experiment demonstrated when I was an undergraduate. In fact, it's a very old experiment. It was first done in 1909.
This is our light source for the experiment. So the light is being steered by these mirrors onto the slits here. And there's two slits in this slide, and that produces the Young slits interference pattern, which we see on the camera.
The interference pattern is the set of faint vertical stripes at the center of the red spot. These only appear when two slits are open.
One slit, two slits. One slit, two slits.
With two slits open, the single beam of light is split into two beams which overlap like ripples on a pond. In some places, the ripples reinforce each other, while in others they cancel each other out, creating the pattern of stripes on the screen. But what happens if the intensity of the beam is reduced by a filter so that only one photon at a time can reach the slits?
Now, you can't see the beam at the moment, but if I introduce some nitrogen, you should be able to pick that up. So now you can see the beam scattered by the nitrogen, but you see nothing after the filter. The filter essentially stops everything we can see. But the camera can pick up the few photons that are arriving.
The photons arrive at the slits one at a time, so those that get through and reach the screen on the other side should form just two bright lines. They shouldn't interfere and produce the full pattern of stripes, but they do. And this is how the stripes appear on a computer screen.
When one does the experiment with individual photons, the pattern that builds up after one has passed many photons through the apparatus is exactly the same as it was in strong light.
And that's something we just don't understand.
As an undergraduate, we were told, oh, this is because the photon behaves partly as a particle and partly as a wave. Now, that just doesn't make sense. It's gibberish. It's saying that the photon is both in one place and spread out at the same time.
Deutsch believes that the single photons are producing the full pattern of stripes by interacting with other photons that we can't see.
The photon that we can't see is a photon in a parallel universe, a nearby parallel universe, which is interacting with the photon in our universe and causing it to change its direction. The result of the single photon interference experiment is the strangest thing I know. It is conclusive evidence that reality does not consist of just a single universe, because that result could not come about unless there were another nearby universe interacting with ours.
If true, this idea has profound implications for time travel.
When one travels back in time, one does not in general reach the same universe that one starts from. One reaches the past of a different universe.
Could this explain why we haven't met any time travelers?
I don't believe it personally, mainly because this idea is not very constructive. There are not many consequences of this idea which we can test in a real experiment.
I think we can't say for certain, but if I had to lay my bets, and I like to lay bets, I would lay my bets on the simpler non-parallel universe resolution.
Another person who likes to lay bets is Stephen Hawking. He and Kip Thorne have been betting on the nature of the universe for years.
This bet here is probably the most famous one. It was a bet I made with Stephen Hawking in 1974 over whether or not Cygnus X1 is actually a black hole. And Hawking, after 16 years of this bet sitting here, finally conceded. Stephen Hawking and I have occasionally discussed making a bet over whether or not the laws of physics permit you to go backward in time. We haven't been able to conclude a bet because almost all the time we're on the same side of the issue. We both think it is probably impossible.
Stephen Hawking has been skeptical of time travel for years, but even he cannot rule it out for sure.
To make time travel possible, one seems to need both general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs very small scales. These two theories are inconsistent with each other as they stand, so we have to find a new theory that combines them.
Cosmic relationships, like the motions of planets, are governed by Einstein's theory of gravity, general relativity. But these laws do not work on the subatomic level, just as the laws of quantum mechanics do not work on the larger scale. So physicists are searching for a way to unite the two in a single theory called quantum gravity. This is the holy grail of modern physics, a unified description of the nature of space and time on all scales.
So I would like to discuss the Big Bang.
Scientists are still in the process of crafting this theory, and whether quantum gravity will permit time travel through a wormhole is unclear. Yet, they can't resist speculating.
When you try to make a time machine out of a wormhole. Having discovered that it is possible, according to general relativity, to take a wormhole with two mouths and turn it into a time machine, my students and I then searched for some way, some mechanism to prevent this from really happening in the real universe, because we thought it was ludicrous. You shouldn't be able to do that. And we actually found a mechanism that, in fact, we were able to show always intervenes whenever you try to make a time machine. Suppose that I have two wormhole mouths that I'm going to turn into a time machine. Of course, I do it by taking that mouth and sending it off at high speed out into space. It turns around and it comes back, and just as it's on its way back, it suddenly becomes a time machine, and one can travel through it and get back before one started. Right as it's coming back and settling in, just before the moment when it can become a time machine, suddenly, according to calculations we've done, it explodes. Poof. No more wormholes, no more time machine. The question is why? What made that happen?
What seems to happen is that particles can keep coming round again to the same event in spacetime. This makes the energy density very large, which warps spacetime so that travel into the past is no longer possible.
Birth of the universe.
It seems that energy might pile up inside the wormhole until it self-destructs.
You get, in fact.
But when Thorne applied what is known of quantum gravity, the picture changed again.
It appeared to us that just as that mechanism was about to, in fact, make your time machine explode at the moment you're trying to activate it, right at that moment, our calculations would fail because the new laws of physics, the new laws of quantum gravity would take over, and the techniques we had of computing what happens would no longer be any good.
So perhaps quantum gravity might allow the time machine to exist after all. Thorne decided to see what Hawking made of this.
He got rather disturbed because Stephen is a defender of the establishment. And he really believed that this really would be the mechanism to prevent you ever from making a time machine, and said they've not correctly read the tea leaves of what quantum gravity is going to do. Ultimately, after going back and forth with Stephen several times, we converged to an agreement that he was probably right, we were wrong, the explosion probably will destroy the time machine. But we can't be absolutely sure, we won't know absolutely for sure until we have the full laws of quantum gravity in our hands and we can explore just what they say about the endpoint of the explosion.
In the meantime, Hawking remains skeptical of time travel, a belief he puts forward in what he calls the chronology protection conjecture.
The chronology protection conjecture would make the work safe for visitors.
The most likely mechanism that would enforce Hawking's conjecture is the explosion of the wormhole. But this is just a conjecture.
It's a kind of informed guess, which may be mistaken. That's what a conjecture is. And the word conjecture in mathematics is often used as a challenge to future generations to try to prove or disprove.
It's not a principle, it's not a theorem, it's a conjecture because we do not yet know for certain that there is a mechanism in nature that will always enforce it.
Well, if you ask me, do time travels really be possible in the future? I must give the positive reply. You see, it will be possible.
I do not see a way to make time travel possible. However, if I heard that somebody else some other country was doing this, I think I might plunge into the game.
I myself believe that there will one day be time, because when we find that something isn't forbidden by the overarching laws of physics, we usually eventually find a technological way of doing it.
I believe we will know in 10 to 15 years when we have the full laws of quantum gravity in our hands. My best guess, and I would be willing to lay a fairly heavy odds on this on a bet with Hawking, but he won't take the other side. My best guess is that when we have those full laws in our hands, they will say, no, you cannot make a time machine and go backward in time ever. But until we have those full laws, we just have to leave it as a possibility that remains a possibility.
I wouldn't take a bet against the existence of time machines. My opponent might have seen the future and knows the answer.
The following is a conversation with Don Lincoln, a particle physicist at Fermilab, who has spent decades working at the frontier of high-energy physics. This was a mind-blowing and inspiring conversation. Don turned out to be one of my favorite people to talk to about physics. Truly a unique mind with that rich and Feynman ability of taking very complicated ideas and explaining them simply, without losing any of the essential brilliant insights at the core of those ideas. This is a Let's Frequent podcast. To support it, please check out our sponsors in the description, where you can also find ways to contact me, ask questions, get feedback, and so on. And now, dear friends, here's Don Lincoln. In describing the search for a theory of everything in physics, you describe the history of physics can be told effectively as a kind of history of unifications. There's this centuries-long quest to show that these distinct phenomena are actually linked by some unified underlying principles, even starting with Newton, that you could think of the effort of physics as one as trying to unify the laws of nature. So I was wondering if we could talk through the history of unification, that lens of physics.
There are, of course, lots of different ways to do physics, but the way that I would say that particle physicists, cosmologists do is they are trying to really find basically the underlying principles that govern the laws of nature. If we go back, say, to the, 1650s or so, you're the most brilliant person around, and you've noticed two things. One you've noticed is that when you trip, you fall. That is the nature of gravity that we all experience day to day. But then there's sort of astronomy, where you look out at the heavens and you see the stars march across the sky. You see planets move through the stars. And that seems to have absolutely nothing to do with what happens when you drop your sandwich and the dog grabs it from you. So the brilliant thing was when Newton looked at that and he thought about maybe the moon is falling, but it's missing the Earth. So what we had is that in maybe 1650, you had what we might call the laws of celestial gravity, the gravity that governs the heavens, and terrestrial gravity, the gravity that is here on Earth. Now, we don't think of it that way anymore. We think of it as just gravity. But at that time, that wasn't at all obvious. And in fact, if you look in the books, Newton's theory is Newton's law of universal gravity. The universal is there, and the reason is because he realized these two things that seemed to have nothing to do with one another were indeed one and the same. I mean, this is absolutely brilliant. I mean, Newton is arguably one of the most brilliant humans of which I'm never aware. But at any rate, it is the first sort of easily to describe unification of physics that you can state in a way that sort of makes sense to modern humans. I mean, you can go back farther than that, where people are talking about chemistry, the nature of atoms. You go back to Democritus, who was wrong about very many things, but the idea that there was a smallest particulate form of matter is right. So it's kind of funny, you read the chemistry books and they say that the idea of atoms goes back to Democritus, and his idea was that, like,
there was a smallest atom of oil, which was smooth. And it was smooth, of course, because, well, oil is smooth. There was a smallest atom of vinegar because vinegar is tart and it pricks your tongue. So therefore, atoms were little sharp, pointy things. And so he was wrong about a lot, but he was right about the idea that there was a small particle. And we now know we have a very different concept than he did. So you can go back farther than that. But getting to unification, there are more examples. For instance, if you go back to, say, 1830 or so, scientists were trying to understand electricity, for instance. And there was a lot going on. People really understood things. But at the time, you would have two phenomena that are familiar to us now. One is a magnet, which, at the time, mostly magnets were simply a piece of wire that had been magnetized and they could stick to steel. And then you had electricity, which was, at the time, they were generating little sparks that they could play and have fun with. Or, more broadly, a lightning bolt blazing across the sky. And so when you think about this, that lightning bolt and that little magnet seem to be really unrelated. But over the 1800s, a number of scientists were exploring little aspects of what happens when you run electricity through a wire. It seems to make a magnetic field. They did a whole bunch of experiments, and there were a lot of names. But in about the 1860s or so, James Clerk Maxwell took all of those ideas that had been percolating around for the previous 50 years and wrote his laws of electromagnetism. And they're really fascinating. If you look at the laws of electromagnetism, they're differential equations or integral equations. But basically, what they say is on one side you have a bunch of terms that have electricity in them, and then you have equals on the other side, a magnetism thing. So forgetting all of the mathematical symbols, you have electricity side equals a magnetism side. Electricity equals magnetism. And that is a staggering concept. The fact that these two things, the lightning bolt and the magnet that holds your kid's heart to the refrigerator, are the same. And this was another case where electricity and magnetism became unified into electromagnetism. So now we have two examples. One, gravity being unified, terrestrial and celestial gravity, and then electricity and magnetism. So I'll tell you about some more in a moment, but one thing that's kind of important, because the goal is, of course, to unify everything. That if I could do what I want to do, it's a unified theory that would explain how behavior follow energy, matter, space, and time, which is a grand goal.
And I would say that maybe one of the goals of science more broadly outside of physics is to construct models that can generalize the world. So if you look at Darwinian evolution, that was a very beautiful theory that captures another layer of reality of like how this particular thing that we see here on Earth happens.
Right.
So when we talk about the theory of everything in physics, that's capturing a different layer of abstraction about the functioning of the universe.
Right. The whole Darwinian evolution, the fact that our genetics has a significant overlap with the genetics of a banana is pretty staggering. It's astonishing that works. So that is amazing. But for at least the class of scientists that I am, what we think of is, well, sure, biology is interesting and all, but when you get right down to it, it's caused, whatever happens in biology is caused by the movement of molecules. And then you say, well, that's great and all, but molecules, they do what they do because they're made of atoms. Mm-hmm. And then the next step is, well, atoms, that's great, but atoms work the way they do because of the nucleus and the electrons. And then the nucleus is protons and neutrons. And so there are those of us, myself included, who want to dig down to the very, very bottom and find out what is the smallest building block of nature from which all of these other far more complex and interesting and abstract things are. But what is at the very, very bottom? And also, that's great, but if you know what the smallest building blocks are, that doesn't tell you the story. It's like having a whole bunch of Legos, but not knowing how to put them together. You also need to know how they interact, how they work. And so that's what we study forces. So there are the various subatomic forces of which we're familiar. And for instance, electricity and magnetism are components of electromagnetism, which then governs the behavior of things like, this is amazing, electromagnetism explains, of course, electricity, magnetism, but it explains how light works, it explains how much of chemistry works. So electromagnetism, 1860 or 70, the wonderful thing about that is if you take Maxwell's equations and you apply a little bit of calculus, it's very easy to see that the laws of electricity and the laws of magnetism combined together make what's called a wave equation, which that shows that these electric and magnetic fields oscillate, they vary. And if you have something that's varied, that's a wave, and the wave then moves. And if you do the math, you find out that the speed at which these waves move is the speed of light. And so people said, wow, the speed of light comes out of those equations. And that had to be, I think, very persuasive. And of course, electromagnetism also plays a really significant role in chemistry, because after all, atoms are held together by electromagnetic forces. There's more to how atoms work. There is all the quantum mechanics stuff. But if you did not have electromagnetism, or if electromagnetism was very different, then atoms would be very different. So it plays a very big role in holding us together. So it's a staggering advance in science to have a good behavior. And of course, being able to tame electromagnetism is why people can hear you when you do your podcast, because through the miracles of the internet, just electricity running the computers. I mean, this is a case, if I could get on a small soapbox, where people back then said, well, why are you messing around with magnets and sparks and who cares? Well, that very fundamental digging into the laws of nature has spin-offs, and it has spin-offs. One of the big spin-offs is our entire technological society. Without being able to govern electricity, we'd still be farmers and shoemakers in cities, but we certainly would not have everything that we do. So, off my soapbox. But it's really a lovely thing to show how this digging into deep, fundamental, not understood, mysterious things can, 100 or 200 years later, transform the world. And the type of science I do now, people often ask, well, what good is knowing about how the inside of atoms work, how the inside of quarks work? And I don't know the answer to that, but just being a little more pragmatic, if I go back, say, 100 years, where people were trying to understand how the protons and neutrons inside atoms held together, how they split, how you could combine them and so forth, this has led to nuclear power. Now, whatever you think about nuclear power, and some people like it and some people don't, but it is powerful. It will generate energy for humanity, and it may be that is the path that we take as we move away from digging fossil fuels out of the ground. Humanity is going to need power, no matter what. Nobody is going to go back to the way things were in the 1700s. And one enormous source of energy that is there for us to take, if we so choose, is the modification of the nucleus of atoms. Seem to have absolutely nothing to do with anything, and yet it provides humanity with an opportunity, which of course requires that we think carefully of how we do that, and if we want to, but it gives us something that we didn't have before.
Yeah, it's very clear that nuclear fusion and nuclear fission will unlock a huge amount of energy that's required for civilization to flourish, but that's almost like near term. Longer term, you can think about things like, we'll talk about dark energy crisis and antimatter. Maybe if you figure out some of the mysteries around antimatter, that too would lead to energy sources, how to produce energy. That too might lead to counterintuitive propulsion systems for us humans to travel through the universe. Now, right now, it seems far-fetched, too expensive, too complicated, too difficult, but breakthroughs in the fundamental theoretical physics might lead us to unlock some incredible energy sources, incredible technologies that will allow humans to explore the universe. And of course, we should also mention that as always with technology is a double-edged sword. It will most likely lead to the development of more dangerous weapons or other sources of harm. And then we, as a civilization, kind of have to walk that line and hope we figure out how to do more good than bad with the technologies we build.
Right. But we have to really remember, while people worry about nuclear weapons, which are admittedly very dangerous, and even nuclear power, which has waste that has to be dealt with, what science is doing is working out, finding power that nature has presented to us. This is not new. Fire is like that too. Fire can burn down your house or it can cook your steak. Power is like that, and that's just something that we have to understand as humanity, and that's why this needs to be when we talk about science, it has to be a broad conversation by all of society, because what scientists can do is figure out how the world works. Society has to figure out how we wish to apply that or not apply that.
Also, solving the mysteries and the puzzles of the universe in itself is effing awesome.
It is. It is.
So, I mean, that's the thing that makes us human in part, is looking at a thing and saying, how does this work?
Sure.
And then together, a bunch of apes get together, like poke the thing, kind of shake the thing.
Yeah.
And then over time, you have rockets going out into space. You build roads and bridges. You build the internet. Anyway, so we talked about Newton. We talked about Maxwell. That takes us in the 20th century in terms of unification. There's a guy named Einstein, on whom you were quote,
Fibula Travel. To je odmor.
The effort of unification.
Sure. So Einstein, he's a pretty amazing guy. In 1905, he had his miracle year where he wrote multiple papers. The one that most people know about is special relativity, where he showed something that makes no sense to anybody who's not really dug into it very hard. And that is that two people experience time differently. Time, is a fascinating thing. We don't really understand what time is, which is weird. You think that that'd be something you understand very well. Know a lot about it, but really understanding it, not so much. But Newton thought that time was just universal for everyone. So my time, your time, some person's time on Mars or on Alpha Centauri, everybody experienced time the same. What Einstein showed was that that wasn't the case, that different people moving at different speeds with respect to one another experience time differently, which is absolutely a mind-blowing concept. Now, most people think that Einstein then said, well, he invented space-time, that space and time are the same thing. And he was behind that, but that actual insight came from one of his teachers, a guy by the name of Minkowski, who looked at Einstein's equations. Minkowski was a little bit more mathematically inclined than Einstein, and he saw that if you look at the equations, you have basically one person's space and time equals some numbers times this person's space and time. And so that's kind of a staggering thing. So that is where Einstein and Minkowski really did this unbelievable concept that space and time are actually pretty much the same thing. That runs afoul of our understanding of how the world works, because time just moves, it's continuous. We know what it is at a visceral level, in an experiential level. We might not understand it at a formal level, but we know what time is. It's what makes today today and not yesterday or tomorrow. Space is a little different. You can walk somewhere, you can walk back, you can move around. You have more freedom to move in space than you have to move in time. You can always move forward in time. It's just moving backwards that turns out to be a little more difficult. But yeah, Einstein's understanding that that is the case, it caused everybody to think about the world very, very differently. And that was in 1908 when Minkowski really laid it out in a strict space-time.
And that also led to the work on special relativity, led to the speed limit, the speed of light.
Well, it was a premise. He had two premises. One was that the laws of nature are the same for everybody. So if you're moving at some speed, or if I'm moving at some speed, I can say I'm not moving and saying you're moving at some speed. That's not controversial. That is what we call Galilean relativity. It's from hundreds of years ago. But what Einstein said that was controversial was that everybody measures that the speed of light is the same, irrespective of how we're moving with respect to each other. You'll measure the speed of light to be a number, I'll measure the speed of light to a number. And that's very, very different from what Newton would have said, or Galileo, or any of the old guys. And it was taking those two things together that caused all of the weirdnesses of special relativity. Now, you could then very easily say, well, that second premise that everybody measures the speed of light to the same is just dumb. And you could test that. So that's where testing relativity comes in. And Einstein's equations, which include those two assumptions, it predicts the behavior of everything perfectly well. Now, we've actually measured, done experiments where we can say that the speed of light is the same for everybody. That's not how that's been in the beginning. It was really that assumption leads to predictions. The predictions are true, so the assumption is true. Now, there is for those people, for your viewers who want to say, well, how do you measure that the speed of light is the same for everyone? The particle physicists do this. And the way you do this is the following. There are some subatomic particles that, when they decay, they emit light. That's their decay product. And so you collide two things together so you know when the particle was created. Then you have surround your collision point by a detector, and you measure how long it takes for light to get to your detector, and by God, it's the speed of light, which it should be. However, sometimes in these collisions, some of these subatomic particles you make are coming out at very high speed. They might be coming out at 95 or 97, or a very large fraction of the speed of light. And then they decay into photons. And so you measure how long it takes for the photon to get to your detector, and it says that light travels at the speed of light. Now, if it were that, if Einstein's conjecture was incorrect, you'd have a particle coming out at near the speed of light, it would be decaying into a particle traveling at the speed of light, then that particle should have traveled at, say, 2 times the speed of light or something like that, so it should have taken half as much time to get to the detector, but it doesn't. So this is a hard, serious measurement that shows that something, we can measure the speed at which light comes out of this stationary created particle, and it's the speed of light. Then we can measure what the speed is of it coming out of something that's moving, and it's still the speed of light. So that is an actual measurement, but that is not something that was possible in Einstein's day, but it is now.
Just to take a small tangent, how weird is it, in the full ranking of weirdness that is physics, how weird is it that there's that speed limit of this speed of light?
Well, I have to tell you, when I first encountered this, it's pretty freaking weird. It's like pegs the weird meter. But as you become more familiar with it, as you become more comfortable with the idea, the thing to remember is the speed of light. It's the speed of light through space-time. Once you embrace that, that makes a whole ton of sense. It all of a sudden makes everything fall much more into place. I think that there is an ultimate speed isn't that shocking. It just simply says that it's a property of space, in the same way that there is, space can transmit a certain strength electric field. It can support a certain things. Whatever space is, and we don't know what space is, but whatever it is, it has the capability of transmitting these things at that one speed through space or time, and everything else comes from our insisting that we keep space and time different. That's how I view it, and at least for me, that once I accepted that, it all became very comfortable.
So the nature of my question actually here that will apply over and over is trying to empathize, trying to put ourselves in the shoes of the people before space and time were unified into space-time, and really experience and think through how difficult of a leap is that.
Huge.
The reason I sort of say that is we are now in the modern day, in the 21st century, and of course we're going to have to make leaps like that in our future. Mm-hmm. So what are the unifications we're not seeing in front of our eyes. So, for example, there's so many examples through your work, through your lectures, of Paul Dirac taking antimatter seriously, looking at what the math shows and saying, I really think this thing exists.
Right.
I mean, it just sounds insane.
It does.
So I think this is a good warm-up. The space-time unification is a good warm-up as we march through the 20th century, because it gets, in my view at least, weirder and weirder, even with Einstein himself.
Well, let me give you an even more basic example. Sodium and chloride. Sodium is an explosive metal. You put it in water, and it's kind of neat. You put it in water, and it doesn't quite explode, but it gets hot, and it pops around. Chlorine, it's a gas. It's going to kill you. So these two things are deadly. They're awful. And yet when you mix them, you put it on your food at night, salt, right? And so this is a case where this whole A, unification, and B, this deeper understanding, in this case of chemistry, of how two things that are dangerous can be brought together and turned into something not only innocuous, but necessary for human life. And so this is not unusual, what you're describing. I mean, when you think about it, forget about everything else, just the fact that, we tell little kids, that the world was made of atoms. Now, that's crazy. Most people have never seen atoms, and yet nobody really doubts it anymore. And I think it's just a case of familiarity, and then the culture slowly accepts it, and it's real, even without the evidence. In fact, one of the courses you described there, how we know what we know, I think that's a valid question. How do we know there are atoms? And of course, there are ways we do.
And by the way, on that front, I would love to go through how we know the building blocks of the universe as we march towards quarks. That, in the course that you mentioned, is one of the most fascinating things of this philosophy of atoms being around for a very long time. Then you concretize and you actually can prove or have strong observations that indicate that there is atoms, and then there is a nucleus, there is electrons, there is photons, there is quarks and leptons. I mean, it gets weirder and weirder, and now we're facing the mystery, is this building blocks even smaller than that? But anyway, Einstein, turns out, didn't just do special relativity. By the way, I really think he deserves 3 Nobel Prizes. He got it for photoelectric effect. The fact that he didn't get it for general relativity is a crime against humanity. I don't understand. Obviously, he should have gotten it for general relativity and special relativity. I mean, I think special relativity is separate from general relativity as far as Nobel Prizes go. So, general relativity is another unification.
Yes, that's right. What Einstein realized was that if you were in a rocket ship and the rocket ship was a very quiet rocket ship and it was accelerating, you would feel like you were experiencing gravity. And so, as you say, it's one of his happiest moments when he realized that acceleration and gravity feel very much the same. What I'm impressed by is that idea, which is already a pretty neat idea, somehow led him to take his space-time idea, take this acceleration gravity idea, and realize that he could describe gravity as the bending of space-time. Space-time being constant, like east-west, north-south, that's already hard enough. But now he's saying, well, take your map and crinkle it and bend it and so forth, and that's gravity. And that is a staggering, mind-blowing idea.
I wonder if you can comment on what do you think is the idea generation process that leads to that. So probably an Einstein case, just to start with, what if gravity is itself space-time geometry? You have to have a thought like that, right?
Yes, I think so. There's a lot about science. There's, of course, knowing what went before. There is knowing the mathematics that allows you to figure out the implications of your theory. There is the discipline to argue with yourself and other people because most ideas are wrong. But then there's what you just described, that intuitive spark. And that is something that is very, very difficult to create. There's a reason that we venerate these people, is because it is an unusual feature, and most people only have that aha moment once in their lifetime, if they have it at all. And then there's a tricky business, because I'm sure you do, and I get a lot of letters from creative thinkers who don't have all of the history and the mathematical discipline and the self-critique that's necessary. And so they come up with these ideas, and often it's easy to see where they just don't play out. So in order to be that person who changes the way we see the world, ideas themselves are not enough. These creative ideas, that's not enough. You need it with the discipline and the critique, and it's that amalgam of those things that make you a genius that history remembers.
But it's hard to know. In a field of people you might be tempted to call crazy, there could be geniuses there, and it's hard to know which is which. We should mention that Einstein himself couldn't see the genius in quantum mechanics initially. Couldn't see the correctness, I should say. So he could see the insanity of gravity bending space-time, but quantum mechanics was too weird for Einstein.
In all fairness, it's weird for me too. But the thing is, even while that is true, and Einstein maybe spent the last few years of his life trying to blend electricity and magnetism and gravity in a single thing, and he was unsuccessful. But he still was a very, very valuable critic of quantum mechanics. It's not that he didn't understand it, because he did understand it. He thought about the implications and all this quantum entanglement business, not all of it, but he was responsible for saying, well, if you're right, then this. And of course, then people went out and found out that Einstein's implication of quantum mechanics was real, and so they could say, see, quantum mechanics is real. So, he was thinking deeply about it, and he was doing exactly that thing I said. There's that spark idea, but there's that critique idea. Mm-hmm. And if you're able to critique an idea, you might kill it. And it's always depressing when I have this brilliant idea and it gets killed, but it's better to be killed than to keep it around and waste time on it. And so he was, in that case, not generating the aha. What he was saying is, all right, let's take your aha, let's see it's right. What does it mean? It means this. That allows people to go test it. And so he was contributing very crucially to that other part of scientific advancement, which is not just the aha moment, but the beat it to death, test it, critique it, and make sure it's real. And it's only after all of that has been done that you really are sure you're right. And that's why science is such a powerful tool. It is that combative, just downright kind of jerky critique that most people don't like. They don't like people saying, your ideas, might be wrong. But it is crucial. It's a crucial part of the scientific process.
Plus, there's that quote on the other side of it that I've heard you mention, which is, I believe your idea is crazy, but is it crazy enough? Or was that Niels Bohr?
Yes. We all agree that your idea is crazy, but is it crazy enough?
And there is some degree of taking those leaps of crazy, but it has to be backed with rigor.
Right.
And the unifications continue that as we take steps towards the standard model, which is such an incredible part of physics in the 20th century. So can you describe that unification?
So, we're sort of jumping forward here now to the 1930s or thereabout. And by that time, people had realized that there are 4 distinct forces that do not seem to be connected. One is gravity. 2 is electromagnetism, and those are things people are relatively familiar with. But there are 2 other forces that only have any real importance inside the nucleus of atoms, which is why most people have no experience with them. One is the strong nuclear force, which holds the nucleus of the atoms together. And the other one is what we call the weak nuclear force, which is responsible for some types of radioactivity. And since most people don't play around with nuclei, and most people don't play around with radioactivity, they don't know what that is. But by the 30s, scientists had done enough experiments, done enough theorizing to say that there were these four forces. And that was already a triumph. I mean, in our goal for a theory of everything, we'd like to think that there is one force, which is what we're talking about, the unification. Maybe these four forces are just different ways of looking at a single underlying force. But in the 30s, that's where we were. There were no four forces. So we move ahead, and in the late 50s and early 60s, some people were thinking that maybe the weak nuclear force and electromagnetism actually were the same. So they were working on trying to bring together these two forces to show that they're connected. And it came true. They were able to show that electricity and magnetism were actually two different facets of a single force that we now call the electroweak force. Mm-hmm. Now, the story that you're told in articles about this, about what people have called the Higgs boson or the God particle, the story is very, very simplified, because in 1964, there were three groups with 6 individuals who came up with important papers talking about what's called the Higgs field. And I'll get to what that is in a minute, but the Higgs field is important. But it wasn't until 1967, so 3 years later, that Steven Weinberg and some others actually unified electromagnetism and the weak force.
Sheldon Glashow, Abdus and Steven Weinberg successfully unified electromagnetism and the weak nuclear force, that showing that at high energies, these two forces were merged into a single electroweak force.
Right, and that was in 67. All right, everybody talks about this thing happening in 64, but it really wasn't. It happened over quite a few years, actually. But, all right, so now what you said is true. So Weinberg, Glashow, and Salam showed that electromagnetism and the weak force at high energies were the same. There was a problem, however, and the problem is that electromagnetism has an infinite range. And we know that because we can see stars that are millions of light years away. That shows you that the range of that force is essentially infinite. The weak force, however, basically becomes non-existent on distances much smaller than the size of a proton. So that, to say, oh, they're the same, and yet one can reach across the universe and one can't reach out of an atom. Well, that's just dumb. I mean, the obvious thought here is, well, we just proved that whole idea is stupid, so throw it away. Ridiculous. And that is where these ideas from 1964 came in and saved the day. So how can it be true that the electroweak force is real and electromagnetism and the weak force act so differently? The way that could happen is if these forces were transmitted by a particle moving from one subatomic particle to the other. In the case of electromagnetism, it's the photon. In the case of the weak force, we call them now the W and Z particles. So the idea is that Higgs and his colleagues came up with is saying, all right, the electroweak force is real. The way we make it so that there is now an electromagnetic force and a weak force is the force-carrying particle of electromagnetism has no mass. The force-carrying particle of the weak force has a mass. And so what was done is a field was postulated, that there was this additional field that was kind of distinct from this electroweak field, and we call it the Higgs field. And the Higgs field permeates all of space. And here's the kicker, some particles interact with the field, and some particles don't interact with the field. The ones that interact with the field get mass, and the ones that don't interact with the field don't have mass. And so that's the idea, is that the Higgs field gives the weak force particle's mass. However, the photon laughs at the Higgs field, doesn't see it, and it has no mass.
And I should say here, going to perplexity, the big picture view, the Higgs field is the quantum field that fills all of space and gives many elementary particles, just as you're saying, their mass through their interaction with it. The Higgs boson is the particle associated with ripples or excitations of this field. In modern particle physics, every type of particle corresponds to a field that exists everywhere. The Higgs field is one such scalar field, meaning at each point in space it has a single numerical value rather than a direction. The Higgs field differs from most other fields because even in empty space, empty quotes by the way, empty space, its average value is not zero. This non-zero vacuum value is what enable it to endow particles with mass.
Right. So let's talk about something a little more familiar, just to try and hang some intuition on those words. All right. So right in front of us, there is a gravitational field. Now, you can't see it, but right there, check it out.
Yep.
If I were to take something, a pen or whatever, and put it there, it feels a force and it falls. Very insightful, I know. So we have the gravity field, and we have the pen that has a mass, and the mass and the gravity field interact, and it drops. Now, if we had another...
I have object for you.
All right, so
demonstration purposes.
Performance art. Here we go.
Great.
This thing has mass, and we drop it. How remarkable. It falls. But when we step back and think about what really happens, it's the mass of this thing and the interaction with this invisible field we see here. That's what gives this weight. Now, I have this particle here that you can't see, but it's there. It has no mass. And I leave it there. Well, since it has no mass, it doesn't feel gravity. It's still floating there. And that is really all the Higgs field is. Some particles have effectively what you could call the Higgs charge that interacts and sees the field, and other particles don't. And that is really what you read just basically means. Now, it's kind of neat because in the ordinary day, there is a Higgs field right there, and the Higgs field is not zero, just like gravity is not zero, and things will get mass. But at super high energies, the Higgs field, the strength of the Higgs field goes to zero. So whether things have mass, or whether they have a Higgs charge or not, they have no charge, or they have a Higgs charge, Higgs field zero, they don't interact, it has no mass. So that's kind of what Weinberg and Salam and Glasgow said, is at very high energies, the Higgs field is zero. Since the Higgs field is zero, the weak force particles don't feel mass, and therefore they can travel at the speed of light, just like the photon does, and everything's happy. It is when the universe cooled down after the Big Bang. It was very hot, very high energy, nothing had mass. The universe cooled, and at a certain temperature, what happened is the Higgs field turned on. And at the moment it turned on, it gave mass to the weak force particles, did not give mass to the photons. So that's what we call electroweak symmetry breaking. So it's a mouthful. But all it says is there was a moment in time early in the history of the universe at 10 to the minus 12 seconds after the Big Bang, the Higgs field turned on and particles got mass. So that's the whole idea. So this is another really neat thing. So the electroweak symmetry theory doesn't need Higgs because that only really applies at very, very high energies. But in order to make it work at low energies, you need to fix the theory. And you need to fix the theory by effectively putting a Band-Aid on the theory. Higgs theory is just a Band-Aid on top of electroweak symmetry theory. And that is the Band-Aid that fixes it because it gives mass to particles at low energy.
Well, how does that this Band-Aid, the field, and the Higgs boson come into play on the experimental front, on the evidence discovery front? So what is this Higgs boson?
Okay, excellent. So we have never seen the Higgs field. The Higgs field is a hypothetical, theoretical thing. But that is true of most of our fields. We've never seen the electromagnetic field. We've never seen the gravity field. We've seen the effect of the field. And so all of these theories are now what we call quantum field theories. And that the whole idea of quantum fields. If you have a quantum field, but that field can vibrate like a drum head. And so it doesn't vibrate just exactly like a drum head, but it vibrates locally. So you can have specific localized vibrations. And those specific localized vibrations are the particles. In the electromagnetic field, the vibration is the photon. In the Higgs field, the vibration is the Higgs boson. And so what we can do is not see the field, but we can actually excite the field, make it vibrate, and detect the vibrations. So the Higgs boson idea was predicted in 64, it became useful in 67, and then scientists started looking for it. So in the early 2000s, people were starting to think that we had built particle accelerators more powerful enough to be able to create these vibrations and detect them. So the accelerator that was working at the time was a large particle accelerator outside Chicago at Fermilab called the Tevatron. And we were colliding protons and antimatter protons at near the speed of light at very high energy. And that was the accelerator at which the top quark was discovered in 95. But we had upgraded our apparatus, we had 10 times the number of collisions per second, we had slightly more energy, and we were banging the protons and the antimatter protons together, hoping that we would actually find the Higgs boson.
Can you actually back up a little bit and look at the bigger picture? So Fermilab has this legendary accelerator that there's also a personal story with you connected to it, because I mean there's a million questions I want to ask you, and we'll ask you about some aspects of that. So this idea of an accelerator, the design and the physics of an accelerator, how is that productive for understanding and discovering different aspects of particle physics?
Well, I'm so glad you asked. I mean, this is fascinating. All right. Everybody has heard Einstein's equation E equals mc squared. Nobody knows what it means. Maybe they heard that energy equals mass, mass equals energy. I don't know, But they've heard the equation, the most famous equation in all of science. But buried inside that equation is a really thoroughly fascinating concept that energy and matter are equivalent. And you can, in fact, convert movement energy into mass. And so this is something that we've known for a long time. This was predicted back in basically 1928, so a long time ago, actually almost 100 years ago. And it is not in the slightest bit controversial. We can do this all the time. So the simplest thing is to take two particles that have no structure. So, the closest thing you can have to BBs that are just true mathematical BBs. If you smash those two things together, it's coming in with a huge amount of energy from one direction, a huge amount of energy from the other direction. The directions cancel, so the net momentum, the net energy of this has no motion. So you have these two things coming in with exactly balanced energy, and if they collide, they could stop. Well, that energy has to go somewhere. And that energy can literally create mass, create particles. Now, there are special rules about what happens if you have two things coming together and it creates a particle. It has to create an antimatter particle to balance it. That's just kind of the rules of the laws of nature. Why is that the case? Well, we have some ideas, but in many respects, the answer is because those are the laws of the universe. And that's the things that we try to understand. But this is absolutely true. So what particle accelerators do, among other things, is simply transform energy into particles. And so basically any particle that doesn't exist in nature we can make in this way. You can make the antimatter electron by taking two particles, smashing them together. The energy sits there and it will make an electron and an antimatter electron, and it just does. And we know that the antimatter electron was discovered in 1932. This is all pretty easy. The antimatter proton was discovered in 1955 at the Berkeley Bevatron. And so this is just what you do. You can convert energy into a matter-antimatter particle. Now, the converse goes true, and that's something we might talk about. You can take matter and antimatter and bring it together, and it'll make energy. It's the process can go both ways. Energy can make matter and antimatter. Matter and antimatter can make energy. And this is just true. We do it all the time. There's no question that this is the case.
And we should also mention that this is the reason Fermilab had a nice stash of antimatter particles. So as a side effect, you can also collect antimatter in this kind of way.
Sure.
You can produce antimatter, but is it extremely costly?
Oh, very, very costly. In order, at the Fermilab machine, you would have to smash 100,000 protons into something to make one antimatter proton. So, I mean, it took some work.
Is there some extremely precise recipe of being able to produce particular kinds of particles and all this kind of stuff when you smash two things together? Is there like, how can you control accurately which kind of particles you're trying to produce?
If you want to make antimatter electrons, you smash together energy at a certain... It's just easier with electrons because the electrons, to the best of our knowledge, have nothing inside them. So they're simple. They have a certain mass, and that's that. So if you smash particles together with the right energy, you can make them very, very easily because you can... It's like an old-style radio back in the day where you had to dial it in. You could get right on the station and you could hear the signal, and if you were off a little, it didn't work. The problem for things like protons and so forth is they're not point-light particles. They're kind of like garbage cans full of stuff, and so it's very difficult to make antimatter protons. Now, you can get more of them by increasing the energy at which you collide two particles together. If you're at below a certain energy, and you collide two protons together at kind of low energy, you just don't have enough energy to make an antiproton. And so it doesn't happen. You get to a certain energy, and you can just barely make them. The more energy you collide them together, the more you make. So that is just sort of how it works. More is better.
And then with CERN, if you compare maybe CERN and Fermilab, go to perplexity here. CERN's accelerator, the Large Hadron Collider, LHC, is the world's highest energy proton collider, while Fermilab's current and planned accelerators focus on intense proton beams for neutrino physics, rather than pushing the absolute energy frontier. Absolute energy frontier meaning highest possible energy, smashing of protons together.
Correct. So one, we were talking about like accumulating antimatter.
Yes.
All right. And so that is typically making antiprotons, as opposed to making all particles in general. So let's focus on the antiproton side to begin with. All right. So Fermilab doesn't make antiprotons anymore. We stopped making them in 2011, and it's because we shut our big accelerator down to concentrate on a different facet of particle physics. However, at the time, we would smash protons with an energy of 120 GeV. And in that, we would make antiprotons. So that's a ton of energy. It's true that the CERN accelerator, the big accelerator, is now much higher energy than the Fermilab accelerator was. No problem. But that's not how they make antiprotons. All of these big laboratories, it's not one accelerator. At Fermilab, there were 5 distinct accelerators, and it was basically like shifting an old standard car, because you couldn't just go 0 to super speed in one accelerator. You had to go from one to another, getting higher and higher. Well, at CERN, they use one of basically their second gear in their very big accelerator complex to make antimatter protons. And their accelerator is only 26 GeV compared to the 120 GeV at Fermilab. Fermilab's not operating, but when it was operating, it operated at an energy about 4 times higher than what CERN is doing now. And why is that? Well, it's because what CERN needs to do is to not make as many antiprotons as Fermilab did. They are doing a very different current experimental program. They're doing a fascinating experimental program, including trying to figure out, does anti-gravity fall up or down, which is kind of neat. And we sort of know the answer to that. That's separate. But anyways, so getting back to the antiproton business.
Yeah.
Well, Fermilab doesn't do it now. It was top dog. It's not anymore. The only really big antiproton accelerator creator is a small accelerator at CERN. Okay, so that's the antiproton thing. And if we get back to antimatter, we can talk about that because that is way cool.
Yeah, super cool.
Now, the other side of your thing about making high energy unknown particles, bigger is better. And it is true that the LHC is a very high energy machine. It's about 7 times more powerful in terms of energy per collision. It is also about 100 times more collisions per second than the Fermilab machine. So it is true that the LHC can make bigger, heavier particles that the old Fermilab, the Tevatron, ever could. And that is true. So if you want to look at high energy stuff, yeah, you go to CERN now, which is why many of my colleagues, including myself, once we had measured all of the sort of frontier measurements we thought we could make with the Fermilab accelerator, we saw this bigger, more powerful machine with 7 times the energy and 100 times more collisions per second. We said, heck yeah, let's go work on that. And to give you a sense of scale, the top quark, which is the heaviest particle ever discovered at Fermilab in 1995. There were 2 discovery papers, and the one on which I was a co-author, we had worked for a good chunk of between 6 months and a year of collecting collisions, and there were a lot of collisions. And our paper had 38 top quark candidates, 38. And we knew that half of them were crap, because when you make a detector like that, there's what you call background. So you have the background and the good stuff, and we know it was about 50-50. So we had maybe 19 top quarks after working for between 6 months and a year of collecting data. But now, at the LHC, we make a top quark every second. And that's what higher energy and more collisions per second will do for you. That extra energy, you're above threshold, you make a ton of them, and when you compare the 1995 Fermilab accelerator to the current CERN accelerator, it's probably 1,000 times of collisions per second. So it went from painstaking, pulling teeth to, yeah, now top quarks are a background. We try to get rid of them. There's just too many of them. They get in the way of searching for the stuff we really want to search. They are like so 30 years ago.
By the way, is there something to be said about the kind of signal processing here? How you remove the noise, how you remove the background, how you determine which particle is which. There's probably some like incredible nuance there, even outside of the scope of this conversation.
So let me just throw some numbers out, all right? So at the CERN accelerator, when it's operating, the collisions occur at a prodigious rate. We get about 1 billion, with a B, collisions per second. Now, each one of those, yeah, that's what I said.
Wow.
Now, it turns out some of them are happening at the same time. So there's about, of order, 40 million moments in time per second where you would take a shot. Inside that moment, there might be 20 collisions. So that's why where we get to the billion.
Yeah, but can you individually pinpoint the collisions?
Sort of, to a degree. So the beams are, when people think of beams, they think of like laser beams, but that's not really what particle beams look like. Particle beams look like little tiny sticks of spaghetti, except they're much thinner. They're not as fat as a stick of spaghetti. And they're, at the LHC, different accelerators are different. They're about this long. And so you have one of them going one way, full of protons, and another one going the other way, full of protons, and they pass through each other. And as they pass through each other, you should think of this as like a swarm of bees, and this is like a swarm of bees. And mostly the bees pass through each other and don't do anything. But every so often, some of the bees hit nose on and stripes and wings and everything everywhere.
That's awesome.
And so as they collide through each other, one collision's here and one's here and one's here, and you can't tell too much side to side because the beams are really small. They're sort of the thickness of a human hair, but you can see along the direction that they're, this is about the right size. And so we have detectors around them, and we can actually see, particles came from here and particles came from here, and that's amazing. All right, so at any one crossing, there's maybe 20 collisions. Now, most collisions are absolutely boring. They're boring because they exemplify physics that we know a great deal about already. We've tested it for decades. We know all about it. We don't care. I mean, it's kind of blasé that we can say, oh yeah, we're making 1 billion subatomic particles every second, but who cares because, but that's just the way of, frontier scientists. So what you need is you need to pick out the cool ones, the weird ones, the ones that nobody's seen before. And so what happens is these beams collide, and we surround the collision point within the enormous detector. There are 2 absolutely ginormous detectors at the LHC. One of them called CMS, which is the one I'm on, and the other one is called Atlas, which is the other one, and we don't speak of because, no, they're both really amazing.
Okay, it's good to know that there's friendly competition even inside CERN. That's awesome.
I mean, the fact is they are both amazing, absolutely amazing detectors.
But CMS is just a little cooler than Atlas.
Yeah. I mean, in particle physics, we really absolutely want our competitors to do extremely well, just not quite as well as we do.
Got it. Right. So these 2 giant detectors.
Right. So, but one of them, our detector, the CMS detector, it's the small one. It is 70 feet long, 50 feet high, 50 feet wide. It's 5 stories tall. It weighs 14,000 tons.
Small.
Yeah. Small. Atlas experiment is 150 feet long, 80 feet across. It weighs only 7,000 tons, just a piece of cake. You could take the Atlas detector and you could put 4 of them on a soccer or football field, and it would fill the field up with just enough room on the sidelines for the cheerleaders and the water boy and the coaches and stuff. That's how big they are. So these are absolutely ginormous detectors, and basically they're cameras. And what they can do is they can take pictures 40 million times per second. Now, all the data comes streaming off that detector, and we can't record it all. It would just fill up all of our tapes, and it would be full of all these boring things we don't care about. So what we do is, as the beams pass through one another, we teach our detectors to say, we only want one where there are certain configurations that might be interesting, like there's gobs of energy in the detector, or there's a gob of energy on one side and nothing on the other side, or there's 4 gobs of energy, or whatever. These are called triggers. And so we have this fast electronics that take the 40 million possible pictures per second, and it says, about 100,000 of those are really cool. We should think about them. And then it passes not all of the 40 million, but those 100,000 to the next level, which are commercial processors that have basically our final analysis code, but optimized to run very, very quickly. And what they do is they do a really quick and dirty analysis to say, to further refine what's good and what's not. And that computer farm then accepts about 1,000 collisions per second. And we record those for further analysis. So that's what's really happening. Of the 50 million possible collisions per second, the fast electronics and then the computers pick the 1,000. And then we pass those through analysis software and hand them to the graduate students, and they pick through them, looking and finding the handful that are the next Nobel Prize. So that's how that works. And that is truly astonishing. Hats off to the accelerator builders, the detector builders, the people who make the software work, the people who make the, not gigabytes, not terabytes, but petabytes of data flow around the world seamlessly. Really amazing. I'm very grateful.
So take me to July 4th, 2012, the discovery of Higgs boson.
So this is really fun because the people searching for the Higgs, it's a community, and the entire community knew that the LHC was coming online. So even though many of us had been working on the Fermilab accelerators, a lot of us were transitioning to the CERN accelerator. So we were in the very funny business of wearing our Fermilab detector people hats, trying desperately to find the Higgs boson at Fermilab, while simultaneously wearing our CERN hats, knowing that CERN was going to be able to find it if it existed. And so, we were a little neurotic, kind of wanted, our old stuff to work. And there was an awful lot of people on both experiments.
Did you have a sense that one of the two places would be able to find the Higgs? First, did you think the Higgs boson existed? And second, did you think that these accelerators have the chance to find them?
So I was cognizant of the fact that the Higgs boson might not exist, but there was a lot of evidence pointing in the direction that it might be. I knew that both experiments, the Fermilab accelerator and the CERN accelerator, would either find or rule out the Higgs if it existed.
Rule out?
Well, that's a possibility. I mean, maybe the Higgs theory was wrong.
Yeah.
Right? Until you know it's there, it might be wrong. It's like dark matter. People talk about dark matter. It might not be real. I mean, it probably is, but it might not be.
So you knew at these energy levels you should be able to find Higgs boson.
Yes. So that's the nice thing about this kind of physics, because there was a theory. That theory made predictions. Now, there were parameters in the theory we didn't know. If the mass was this, we get this thing. If the mass was this, we get this thing. But we could do the calculation for every conceivable Higgs mass. And so then we could search. Look, well, let's say the Higgs mass is 100 in some units. Did we see it there? No. Then it's not 100. Well, let's look at 103. Is it there? No. So we could do that. Both accelerators could either find it or definitively rule out the predictions of simple Higgs theory. 100% guaranteed. However, the CERN accelerator had 10 times the collisions per second and 3.5 times the energy. So remember when I said with the top quarks it was like 6 months for 19 versus 1 a second? There's no question. The writing is on the wall. The LHC was going to have an easier time of it if it was real. However, but I'm a Fermilab scientist, and we wanted Fermilab. We want Fermilab to win. Of course. Yeah. So we were busting our butt, and we had done what I said. We had ruled out this region. We had certain mass ranges. We knew it wasn't there, and we finally said if there was a Higgs boson, if it existed, which we didn't know at the time, its mass was somewhere between, if I recall, between like 120 and 145. All right, we ruled out all the other stuff. And so, wearing our CERN hat, we said, okay, we're going to find that. But we were really trying to do it. Now, if we had another 2 years, or maybe 3 years of running the Fermi accelerator, Fermilab would have discovered or ruled out, or in this case, turning out discovered the Higgs boson because it's a real thing. We would have found it without a question. But we didn't have enough data in July of 2012. We needed a couple more years. Unfortunately, in 2008, or unfortunately, the LHC had turned on. It broke. They had to fix it. Turned on again in 2010. It ran poorly in 2011. In 2012, they pushed up their sleeves and said, let's do this. And it turned on. And so, there was this, Fermilab knew if it didn't have it now, it was too late. Anyways, 2012 rolls around, and like 2 days before the announcement at CERN was July 4th. So 2 days before that, Fermilab made a measurement and said, we can rule out certain regions, but certain regions we can't rule out. But what we know, and this is important, if the Higgs boson exists, it must be in this region for which we are not capable yet of ruling out. So that's where we were 2 days before the LHC said, we got it. It was July 4th, 2012.
So detecting the Higgs boson confirmed the existence of the Higgs field, the mechanism through which fundamental particles like electrons and quarks acquire mass in the Standard Model.
Correct. Although, let's be very specific of what we did then. We found a particle consistent with the existence of the Higgs boson. There were alternative theories at the time that predicted not one, but multiple Higgs bosons. So there's a theory called supersymmetry, which said that there was not one, but 5 Higgs bosons. The standard original 1964 Higgs theory says there were 1. And so all we really knew at the time was we found a theory. We did not necessarily confirm that Higgs was right. We found data that said that it looked like Higgs was right, but until we ran for longer, we were unable to rule out other alternative theories. So that's the deal. Now, in the fullness of time, it is, after all, 14 years now later, we have been able to basically rule out some of those other things. And by now, we have validated the things. We found the mass of the particle. We know the spin of the Higgs boson. It has a spin of 0. We have discovered the Higgs boson decays. It preferentially decays into the heaviest particles it can through energy conservation. Can't decay in the top quarks. It's too light to decay into top quarks, but it can decay into bottom quarks. It can decay into W and Z particles. It can decay into a weird way into photons. And we have looked for all of the hypothesized decays of the original Higgs theory, and we have validated that it decays in those ways at the rates that theory predicted. And so now, in the fullness of time, I'm pretty comfortable saying Peter Higgs and Robert Brown and Francois Anglaire and his colleagues, they were right back in the 60s. But we weren't sure on July 4th. All we knew is we found a particle consistent. But the thing is, with these discoveries, they're often just barely discoveries. It takes a while to go and do the more complex, detailed measurements, and that's what we've done.
So at the time, I remember it being called, referred to as the God particle. You also had a minor in theology, so throwing that all together, so calling it the God particle is speaking to the importance, the potential importance of discovering this particle. Do you think that is in some degree justified? Like, if we look at the big impact of it on in the history of physics, how important was it to find and show that the Higgs field is real?
Well, I don't think it is as important as, for instance, Einstein's stuff. I mean, it's an important prediction. Like, the prediction of quarks was very important and interesting in validating this. The Higgs was kind of like validating that quarks existed. It's an important stepping stone, and I do not wish to denigrate it in any way, but there's ones that change the way we thought about the world, like Einstein did. It wasn't that sort of thing. And there is a funny story. So the reason they call it the God Particles is a book by Leon Lederman. And if you read his book, he says, well, you know, we call it the God particle, but we should call it the goddamn particle because it's been causing us so much trouble trying to find it. And Leon ran Fermilab, and he wrote a foreword for one of my books. And I talked to him. He was a really funny guy. And the real truth was, the book was called The God Particle because his publisher thought it would sell more copies. but then that got into the mindset of the reporters and so forth, and we called it The God Particle. Leon never really thought of it as anything to do with religious, or even, he was an incredible jokester, the goddamn particle.
It is a really important part of our model of the universe.
It is.
That there's this field that gives mass to some particles and not others.
Right. It's a huge thing. But it was part of the Standard Model. The Standard Model had known forces, it had known particles, it had all that. The Higgs boson, the one thing that is true is it was the last unvalidated piece of the Standard Model. The Standard Model does not answer all questions, which is why we have unanswered questions in physics, but it was a punctuation point, end of about 50 years of discovery and searching, where we finally were able to say the Standard Model, while incomplete, it's mostly right as far as it goes.
Quick 10-second thank you to our sponsors. Check them out in the description. It really is the best way to support this podcast. Go to lexfriedman.com/sponsors. And now, dear friends, back to my conversation with Don Lincoln. We did a whirlwind tour of the history of physics and took a little tangent on this incredible discovery of the Higgs boson. But we didn't go all the way yet. There's this dream of the grand unified theory, the gut, that is a step towards the toe theory of everything. So can we talk about the gut first? So what's entailed in the gut?
So the gut is short for Grand Unified Theory. We talked about that there were 4 known subatomic forces: the electromagnetic force, gravity, the strong force, and the weak force. And electroweak symmetry unification merged the weak force and electromagnetism into the electroweak force. So what gut hopes to do is to merge the electroweak force and the strong force into one grand unified force. Now that leaves gravity outside because gravity is seemingly fundamentally significantly different. Then subsequently it is hoped that at a higher energy we will be able to blend the theory of everything together with all of the known subatomic forces, the strong, weak, and electromagnetic forces, and then gravity. But so as you say, gut is sort of a way station along the way. That's the goal. And at this point, I would have to say that I do not see a fast progress in the immediate future. I think we're a ways away from that at this point.
You mean on the gravity front?
Maybe we'll come up with something really cool. We certainly had some ideas back in the early 80s that we tested, and they didn't pan out.
Speaking of which, string theory is the thing you're referring to.
Mm-hmm.
So string theory posits that particles are tiny vibrating strings, and by tiny we mean extremely tiny at the scale of a Planck length. Then there's other leading candidates like loop quantum gravity. Maybe there's some alternate theories in the works. Can you linger on that a little bit more? Do you think a theory of everything exists?
So I hold personally that there are rules that govern matter and energy, space, time, and they probably are rules that I don't know. There are probably phenomena I'm not aware of. But I do believe that there is a rule that governs reality. And so in that sense, once we understand the rules that govern reality, the fundamental rules, that would be a theory of everything. You know, there are things that are unknowable, like, for instance, inside black holes. We don't know what's inside there, but that doesn't mean that there's not something inside there. So there's a distinction between what we can know and truth. So I do believe that there are the rules. And I do believe that with sufficient time, technology, effort, we will be able to figure this all out. Now, this isn't a thing in my lifetime. It's not a thing in my grandchildren's lifetime or even their grandchildren's lifetime.
Whoa, that's a pretty strong statement, right? That's a pretty strong statement saying we're 50 to 100 years out from finding a theory of everything.
It took 200 years to go from unifying gravity and to unifying electromagnetism. It took 100 years to go from unifying electromagnetism to unifying the electroweak force. Now you could say, well, gee, that's went from 200 to 100, so it's getting faster. But it's also getting harder because the unification scale is of order 10 to the 15, which we can do the math. That's a quadrillion times higher than the highest energy accelerator we can build today. And it was one thing to, we are reaching diminishing returns. We get something like a factor of 7 increase in particle accelerator energy every 20 years. And so we have to get to a quadrillion times. Now, if you really did believe a factor of 7 every 20 years, then we're talking like 500 years. But, this is like Moore's law that doesn't continue forever. We're not going to every 20 years get another factor of 7. So yes, I think it's a very long time. That's my prediction. Some people are far more optimistic, and we can talk about that.
We should also actually mention that I guess your intuition behind that is not just the part where you come up with a theory that's beautiful and seems to be internally consistent, but you have to have a theory that's making falsifiable, testable predictions.
Correct.
And you have to have a feasible engineering construction, a methodology for creating an experiment that tests that prediction. So I think a lot of this is 50, 100, 200 years from now, intuition is maybe about the second part of that, which is like you need to have an experiment.
Yeah, yes. But, let's say, you alluded to superstrings. I haven't answered that question. I'll table that for a moment. Superstrings is a fascinating idea. I don't believe it, but I love it. I hope it's true. And there's a real, aphorism, and it says you should absolutely never believe what you think. So even if you think superstrings is true, you shouldn't believe it because it hasn't been tested. Now, let's say superstring is correct. I mean, hypothesis, it's correct, 100% correct. I don't know it's correct, so I don't care. I mean, it could be correct, but I don't, until it's validated, it's just a wild-ass guess, so we have to have a way of validating it. So yes, the empirical side of it is important. I mean, you could wake up tomorrow and have the theory that is the perfect theory, but if I can't prove it, I don't care.
If we were to think, this is going back to the great courses on the evidence for modern physics, we're talking about energy levels and tiny particles to the degree where the kind of prediction we would be making is not accelerator type predictions. So it's probably going to be impossible to build an accelerator that detects something like a string. So you have to make predictions about macro scale behaviors.
That's another alternative.
It's a different kind of prediction.
Sure.
Do we even have intuitions about what kind of predictions there would be? So one of the lines of intuitions has to do with black holes or in the singularity. Physics of black holes combine certain elements of general relativity and quantum mechanics, so there you could see some kind of predictions you can make. But you can't really mess with a black hole. It's not like you can create a black hole in the lab.
And the energies that we're talking about, the sizes we're talking about, are inside a black hole, which you can intrinsically never see. So, you can only see the outside of a black hole, not the inside of a black hole. So, what you said, you did say something that was incredibly important and incredibly correct, and probably won't happen, but that's still good. Okay, so we have two choices when you talk about superstrings. Either superstrings are correct and they're making predictions up at the Planck energy scale, at which point we have to somehow build facilities that can generate Planck energies. That's possibility one. Possibility two is this theory, which is currently only applicable at Planck energy scales. Someone figures out a way to take those equations and solve them in a way that, say, predicts the mass of the electron. Right? And that is a tricky business. I am not a string theorist, so I can't tell you that that's likely, but I can tell you that they've been working on it since the 80s and they haven't gotten very far. Furthermore, if I think it's fair to characterize that string theory is still a vague idea, and that's unfair, but let me tell you why I say that. Because what they have are approximate solutions to approximate equations. And that is already saying that we're a ways away from really getting a handle on that. So, yes, if there could be some bright young lad or lass out there, someone listening to this podcast right now, who figures out a way to take superstring theory and solve them in tractable ways that makes predictions from the scale at which they currently apply down to measurable scale today. And if that happens, well, then I might retract my question or my concept. There's a reason why I think that probably isn't true. That's probably not valid. So let me, I love this. All right, so let's back up. I'm going to pitch. I wrote this book for Oxford, Einstein's Unfinished Dream, and Einstein's Unfinished Dream was to come up with a theory of everything. It was unfinished because, well, it's unfinished. And so the second part, the tagline of that book, is practical progress towards a theory of everything, with the emphasis on practical. Because when you read books about theories of everything, when you see podcasts, when you listen to YouTube videos or whatever, they are often written by theorists. And theorists they're big idea people. They're very, very smart, but there's a pragmatism that is often missing, in the sense that they say, well, superstrings, look, have these little vibrating things, and wouldn't it be cool? But you got to get to the, do you know it? So let's pretend superstring theory or something like it is correct. The energy scale at which that should occur is of order 10 to the 15 times higher, 10 to the 19 GeV. We can currently do things at 10 to the 4th GeV, give or take. So that is 10 to the 15. That's a quadrillion times higher energy. So what we are doing now is we are looking at the world with our very best measurements, and we are trying to project out a quadrillion times higher and figure out a theory that explains everything. Now, I have a couple of analogies, but I like this. Suppose that you were some, Joe Australopithecus 2 million years ago or something in Africa, wandering around somewhere in Kenya. All right? You're about a meter in size, so you can walk a meter. Meter scale is like your scale. You can walk 10 meters in every direction, that's 30 feet, no problem. You can work 100 meters, 300 feet. You can work 1,000 meters, that's half a mile. You can work 10,000 meters, that's 60 miles. 100,000 meters is 10 to the 5th, and that's unlikely. But the distance that we need to go from what we can see to the Planck scale, it's not 10 to the 5th, it's 10 to the 15th. So that means, in my analogy, think about this guy who's walking around Africa. Now, if he walks, 100 feet or something, it looks a lot like what it is now. He can make a prediction about what he sees, and when he goes to that new place, it's probably going to be okay. But if he starts walking 500 miles east, well, he, walking around the center of Africa, has no concept of, for instance, the Indian Ocean. He would never predict sperm whales or kraken. He would never predict what it's like the bottom of the ocean is. Going north, he's in Africa. He would never, ever have a clue about the Alps or Antarctica. Going even smaller distances, going a mile up, things wouldn't be very different. But if he goes 10 miles up, he wouldn't breathe and he'd freeze. If he goes 100 miles up, he would die. If he goes 2 miles down, he would roast. The point being is we are like that Australopithecus. We have a realm that we can study, and we can even predict to some validity what would happen if we go some distance away. But the farther away we go, the less and less our local prediction really represents the reality of those more distant times. And so basically his theory about the world would be totally bogus. So even if he had the best theory, his theory would not have anticipated the Alps. It would not have anticipated penguins. Flamingos, not there, And that is just the case. So now, that's what we're doing. We are taking something, and we have reason to understand what we know, and we can predict a factor of 10 or 100. But I think it is the pinnacle of arrogance to think that what we can do, given the understanding that we have from what we've measured now, and predict it out a quadrillion times higher than we can see now. So my opinion, and this is partly because I'm an experimentalist, the correct way to make progress, practical progress towards a theory of everything, is to look around at the things that we don't have answers to right now. For instance, are there something smaller than quarks? I don't know. Is dark matter real? I don't know. If it's real, what is it? I don't know. Is dark energy real? Yes, probably, but I don't know. What is the nature of space and time? I don't know. But these are questions we can explore. And I would expect, and this is my prediction, that, all right, we're going to figure things out at a factor of 10 or 100 times better than we can do now. And we might be able to do that in my kid's lifetime or something like that. But